Thanks for coming. And I'll start. So first I need to thank Adam for hosting me, John for all the bureaucracy, Michelle for when I arrived here, a lot of, I don't know what I'm doing here, and the Harold Schnitzer Visiting Scholar Program. That's the acknowledgements. Then we can start. So dams and reservoirs are crucial infrastructure for modern societies. They provide drinking water, hydropower, irrigation, storage of industrial and sewage waste, and protection from floods. Dams have been around for thousands of years. In addition to man-made dams, natural dams are also existent in mountainous and glaciated areas. Some are a geohazard in today's warming climate. And 2 weeks ago, Erica Medley talked about dams, the risk they pose, and the Cascadia subduction zone from a US Army Corps of Engineers perspective. So what happens when the dams actually fail? And what is the geomorphic perspective? So first, I think that we're now celebrating 100 years for Bretz. And Bretz is our guru. You could see the article at the bottom. 100 years ago, the channeled scabland of the Columbia Plateau in Journal of Geology. So 100 years ago, Bretz found the channeled scabland and started publishing about it. And he's the one that first started telling us that there were catastrophic floods from glacial dam breaks. The Missoula floods that also shaped the Columbia Gorge and the Portland area, as we could see on the map here. In the 1980s, Vic Baker from Arizona, he sort of made the field into more official. It wasn't that there wasn't paleoflood hydrology, but Vic Baker was the one that made it into a subfield of geology, of geomorphology, and made it into a worldwide phenomenon, and it spread all over the world. Here we could see Bretz and Vic Baker. And as we could see, geomorphologists started working on dam break floods. Jim that is here has several of the first ones. John Costa, that was also here. And we could see that there's an interest. And unlike the civil engineers that are looking at the infrastructure itself, we are looking at the river downstream. So why should we care about dam breaks? From a scientific point of view, catastrophic floods are a major process in landscape evolution. In many cases, modern dam breaks allow us to analyze flood events with low recurrence interval that are well beyond the gauge record. And from an applicability point of view, the dam breaks are a major geohazard in an era of aging dams and also of climate change. And the resulting flood determines where the danger zones are. So methods. So I think the methods of paleoflood hydrology is kind of always more or less the same. We're looking for field evidence. High water marks of the flows, as we can see on the top. Slack water deposits, where there's some kind of slow water moving during the flood, where they deposit the sand and create a deposit. If we're lucky, we're able to put dates on that, either with carbon-14 or OSL. Various erosional features, such as tree marks, also within the bedrock itself, sometimes on the sides. And finally, once we're able to build some kind of a picture, connect all the dots into a CFD model like HEC-RAS. HEC-RAS is a river analysis system, and HEC is Hydraulic Engineering Center. So this is a US Army Corps of Engineer model that they're constantly updating, 1 or 2D. You connect all the features that we found in the field, and with cross-section and roughness, put the geomorphic features as elevation benchmarks. I'll show that as an example later. So why do dams fail? So we could see that three different factors are accounting for 92%: overtopping, foundation defects, and piping processes. Overtopping in man-made dams are usually a mistake by the operator. There's not enough storage. Someone is sleeping when there's incoming flood and not doing his job and not opening spillways, and eventually the dam fails. Foundation defects, this is an engineering problem usually. The materials that are making the dam are not stable, and eventually once the water pressure overcomes the material. And piping processes, there's movement of water inside the dike, and eventually it creates a pipe. That pipe enlarges and enlarges, and eventually the whole wall fails. And earthquakes are another factor. Doesn't happen a lot, but happens. And the two last things are burrowing animals and plants and trees, which we could also relate them to usually to piping processes, because they create a burrow, but they are differentiated. And we could see examples of several papers. Jim, that is here, wrote a lot of it. So what are we interested in when dams break? So peak discharge is the first thing. Fully gauged hydrograph is usually rare. Whenever we have a very large failure of a dam, even if there's a hydrometric station, it usually is destroyed by the flood. The inundated areas and transmission losses along the flood course, the channel erosion and deposition, and recovery and preservation. So I will look at the 5 locations. 3 are in Israel, Kfar Yoshua, Nahal Oz, Nahal Hashalim, and here in North America, it's Glacial Lake London in Ontario, Canada, and Glacial Lake Passaic in New Jersey. So this is a table that is summarizing them. We could see in terms of average annual precipitation from basically 0 to 100 in the desert, all the way to 1,300 in the humid Atlantic in New Jersey. We have to say, though, that the last 2 paleofloods are today's climate. You know, the fact that there's more than 1,000 millimeters of precipitation, it doesn't mean that's what happened during the end of the Ice Age. So it has to be acknowledged. Okay, something that is always bothering. The civil engineers are always running to QP of the breach. QP is the peak discharge, so QP. And geomorphologists can contribute to this aspect, as this is an extremely inaccurate parameter used by the engineers. So I'm showing several examples. This is the Nahal Oz Reservoir. You could see it's quite triangular during the evolution of the breach. This is from aerial photos of a plane that was in the air. And you could see it's triangular. And it's an evolution. It's something that is moving. Later, as the flood progresses, it becomes more rectangular when it's active. And once it completely dries up, it's a trapeze kind of shape. So we have this evolution of a shape that is happening in the beginning, something very small, triangular, and it widens up, and there are slumps. And this is something that I want to show you why it's very inaccurate. So you can see the slumps all the time and how it enlarges, and this is after the peak flood already of that specific reservoir. No, so shaky. So imagine this is going on for several days during and after the flood. The QP is already behind us, but it's still enlarging the breach. And if we come to reconstruct we're kind of missing, I guess, we're either overestimated or underestimating, depending on how much sediment was evacuated at the bottom. I think you get the idea. So anyway, this is how it looks at the end. And it's something that is, I'm not sure that is really representative of the peak flow. So this is where something that we are, as people that are working in the field, can do better, I think, than the engineers that are coming to this and making their entire calculations on this. So we'll go through several case studies. Desert climate, Nahal Hashalim, 0 to 100, so hyper-arid to arid. In the Negev Desert, 2 reservoirs, 1 flood defense reservoir at the outlet, failed in 1993. It's a published paper in Greenbaum 2007. An upper mine tailing reservoir failed in summer 2017. And a very large rain-induced flood in October 2004. This is the map. We can see the Ashalim Upper Dam up here. There's barely a basin up here. And the other one is down here. This is already the Dead Sea. So this is where the failed area. This is the lower dam. In the distance, you can see the Dead Sea up in the upper part. This was a sudden failure. This is how it looks from inside the reservoir. You can see the water line. This is walking upstream. And you can see a person at the top. So quite an impressive structure that broke. This is a scabland, kind of how it looks below the dam. Incision of widening of Nahal Hashalim. And this is the Dead Sea here. We'll go to that next. So they were overwhelmed by a huge amount of sediment. This is the conveyor belt that used to work before that. This is the entrance gate. So this was a massive flood that caused a lot of damage. And this is the 2004 flood. So massive damages when you have such events, either natural or man-made. The upper dam, about 100 millimeters. This is inside the reservoir on the left. We could see phosphogypsum, which is a waste product of fertilizer in the Judean desert, just released downstream, killed a lot of wildlife and vegetation, painted the channel in black, $30 million in damages. Peak discharge below that breach was 100 cubic meters per second and attenuated downstream to 40 cubic meters per second at the Dead Sea. So downstream it was not a catastrophic flood, only upstream. In terms of evidence that it left, we could see on the left in the canyon that black layer and slack water deposits. We could see in the open just below the breach when there's a floodplain before entering the canyon. We could see the black layer that is basically the high watermarks. And within the canyon in the bedrock, we could see this, one of our rangers pointing at the high watermarks on the bedrock. This is when it reached downstream. As I said, not something too impressive, a flood, but not very impressive. So a lot of transmission losses along the way and loss of 60% of the flood. And specifically on that, we have a record from a cave of slack water deposits that are dated. And that allows us to create recurrence intervals going back way to a record of 7,600 years. So it all depends on what kind of method, how long is the record that you're using. So 100 cubic meter flood could be a 500-year flood, it could be a 100-year flood, or a 50-year flood. So it all depends which curve you're choosing and what's the length of the record that you're using. And as long as the shorter the record that you're using, the bigger flood it is. So this is something that we always have to think about when we're analyzing the magnitude and recurrence intervals of floods. Are we talking about the gauge record, or are we going back, way back? The Nahal Oz Reservoir, this was during my master's. I said to my supervisor, this is more interesting than my master's. And I want to go there and see it. And so he gave me the department car, and I drove there and spent the next few weeks documenting this. This is a war zone right now, next to Gaza. You could see on the right, before the breach, this was the first fill, so this is a major engineering screw up. You could see the breach after it breached. The first thing that we did was document the high water marks with differential GPS and cross sections. And we could see that during the first 2 kilometers, it started with 1,000 cubic meters per second, and it lost 20% when it reached this small alluvial fan here. So that tells you that there were a lot of losses along the way, and also transmission losses into the ground. In terms of erosion, so this is a massive flood. Imagine that a small gully suddenly receives 1,000 cubic meters per second when the original flow is about 1, 2, the peak flows in that gully. So this is a major erosion event. And we could see here the new in black on the left. We could see the new bottom of the channel bed. We could see the post-flood channel slope and the water surface profile. And basically that tells us that all this gap was eroded. And we can see it in cross-section. This is an example of cross-sections, how it looks. We see these massive walls, almost of a canyon, 5 meters high. We could see the spillway itself, the opening up. You could see the trees that are suddenly hanging in the air after their soil was eroded. So this is a massive event. We're talking about an increase of the area of the cross-section by 60% and 170,000 cubic meters of sediments, of less. This is the alluvial fan that I showed you, the tiny alluvial fan. This is where the first place that the sediment was deposited. We dug several pits there. It was still pretty fresh when we were working there. And the amount of sediment that we calculated was 55,600 cubic meters of new soil. That means that 2/3 of the sediment did not stay in that reach, but left downstream and continued further down. In terms of transmission losses, I think that this is a very extreme case. We could see the one that is dropping. That's the Nahal Oz Reservoir. And you could see other cases of dam break floods around the world, but basically most of them are here in the US. And you could see in most cases the transmission losses are much more moderate. But in this case, after 30 kilometers, the flood was gone. We tried to model it with various models and attenuation curves, and they all failed as they all underestimated. The closest one was an Australian paper that was close, but still didn't hit it. Kfar Yoshua, Mediterranean climate. That's not far from my house. I get a phone call. There's a dam break. Just leave everything and come to see it. And it's exciting, to be honest. So this is quite unusual. It's not a big flood, but still there's a hydrograph because there's a gauging station downstream. So we were able to extract a full hydrograph and see how things unfolded being there and also gauging it. So 150,000 cubic meters were released from this reservoir. The flood duration was 6 days. Peak flood was 17 cubic meters per second. Time to peak was 3 hours, so quite quickly. And time to fill breach was 72 hours. And when I talk about this parameter, as I showed you before, the cessation of earth slumps. So it took 3 days to actually stop those slumps, and 3 hours it took to reach the peak. So that's a pretty big gap. So this is the reservoir again. This is where the movie was. And the engineers and I did not agree on the cause. They said this was overtopping. I said there is no sign of overtopping, but it's root piping. And we could see the Syrian mesquite that is exposed and it's an underground tree that is making these burrows inside. And I think this was the reason for the failure. And they were unhappy with me. Also, a small alluvial fan at the end of the spillway entering Nahal Kishon, some scattered gravels and boulders originating from the dike, seasonal vegetation, also some kind of small scabland with soil erosion on the right. Head cuts. This was a 2-meter head cut that was there before. But there were smaller head cuts as well. We could see the reservoir on top here. This is a new gas pipe that was being put there at the time. And the breach contributed 15% to the eroded sediments of the flood. Again, as I said before, I'm not too happy with those calculations because that's what the engineers do with dimensions. And it always seems to me pretty sketchy. But 15%. In terms of ability to fingerprint the different sediments, it worked pretty well, whether it was the dike's interface, the middle of the breach bed, the nick points, the bed of the breach, the new channel alluvium. So it's possible with the grain size distribution of each place to characterize the sediments. In terms of the actual work with HEC-RAS, long profiles of the bed, water surface, and velocity performed by the HEC-RAS, we could see that there's a place that near the waterfall that there was a jump in velocity, but in most cases the velocity was about 2 meters per second. This is the elevation here. The bed profile nick points show that there was a pre-designed nick point there, the big one. And there was 2 types of sediment. There was the floodplain sediment of the main channel of Nahal Kishon. And then there were, in the distance, this was a cohesive sediment that was eroded. I also did geotechnical tests there, and it quite agreed with what I found, that the cohesive strength of the upper part was much higher than the lower part, which was alluvium. Moving to Glacial Lake London, this was part of my PhD. At the time, Alexis Dreimanis, he was one of the greatest glaciologists of the Great Lakes. And he discovered this lake in the 1970s. And the lake drained into Lake Momi, and it was one of the many meltwater lakes of the Laurentide ice sheet in the Great Lakes of southern Ontario. So this is the Thames River Basin. Everything in Canada is just like in London, in the UK, but in Canada. So the Thames River, the City of London, and Woodstock, everything is copied one by one. Glacial London, this is the period it existed, Lake Momi 3 and Lake Whittlesea era. So this is the approximate times. In terms of field evidence, we found lacustrine sediment on top of the Arva moraine. We could see till, the 2 different types of till, and then the lacustrine sediment on top, which was the highest that we found in the entire watershed. So on the left, you could see here the map that Alexis Dreimanis drew by hand. So this is a very impressive map of all the glacial features of the city of London. And we took this map, and we were able, obviously, to work with GIS and field evidence as well, and build the lake in a much more accurate way and give it volumes, shape, way head into the east, and find all the small bays and just go and look. Unfortunately, most of the lake, when it's not being built on, is agricultural land, and the farmers are erasing the evidence. Even when there's something really nice, like a giant boulder, they put it as some kind of nice decoration at the front of their house rather than keep it in place, which is unfortunate for us. The bowl, its shape, the city of London before it was built in modern times. So this is 130 years ago. The painter, you could still see the moraines. The buildings are pretty small. You could see the river on the lake bed, the two confluence, and they're joining. And this is into the Thames River. And at the end is just before the spillway of the lake. This is Komoka Provincial Park. Fortunately, it's protected, so there were no buildings there. And suddenly, in the middle of a flat area, relatively flat area, you have a canyon, a giant canyon. And it's obviously not something modern of present hydrology. And you know this is something that goes to the past. It's very impressive. Unfortunately, as I said, it's protected. And there's a lot of evidence in that, there's the actual Thames River. It's a pretty big river, but still the valley itself is quite wide around it. And there's numerous things that are not active right now. There are remnants, so erosion terraces, flow marks incised into the glacial drift, benches, berms, mounds, boulders that it's me when I was young. And so a lot of features that are remnants. They're not active now. They're away from the active channel. And I'll show in a second the cross section. And we will see how far away they are from the channel itself. The next thing was to connect the lake and the spillway. So Glacial Lake London, you could see basically it's the city now. Most of the urban built environment. The lake outlet, you could see an artificial artifact here that I had to connect the two moraines. So this is why it's a straight line and not unlike the other topography places. So I had to cut this place where the breach happens and treat it as some kind of artificial dam. These are all the cross sections that we use in the HEC-RAS modeling, all the way downstream to the Caradoc Delta. Fortunately, we have a large dam protecting the city of London. It was built in the 1950s, Fanshawe Dam. And this is creating some kind of false feeling that the city is safe. And it's still being flooded every time that there's too much storage within the reservoir. But it still gives some sense of security. And there's a lot of neighborhoods that encroach into the floodplain. So 60 years of record into the reservoir, and we don't need the dam attenuation, we need the natural flows. So we could see it here from the 1950s all the way to 2014. So minimum discharge is 137 cubic meters per second. The maximum is around 1,500 cubic meters per second in the year 2000. So way after the dam was constructed, there are still large floods, and the average and median discharge are slightly above 700 cubic meters per second. We use this for the HEC-RAS modeling, and we could see on the left the average modern discharge, and we could see that it fills just a tiny canal at the bottom. We start going up to the maximum flood, the modern flood, 1,500 cubic meters per second. It fills this tiny floodplain within the valley. And then we go to the larger paleofloods. So 13,500 cubic meter per second, and we start filling the valley up, and 75,600 cubic meters per second. That's when the highest features that we found. I'll show that in a second. This is the cross-section of the breach that we had to reconstruct. You can see on the left the Ingersoll moraine, on the right the Arva moraine, and the various lines that we generated from modern hydrology and paleoflood hydrology with the het grass. And this is the paleofloods versus the modern floods. We're assuming that there was not a lot of erosion in the river, and this is one of the big problems of paleoflood hydrology, is that we don't know what happened since the flood of reference till today in terms of the bottom. So we're assuming the bottom right now is more or less the same, and there was not a lot of erosion, but there could have been. So we have to have that in mind. So we see modern floods pretty low and reaching 1,500 cubic meters per second. There's a gap in the valley that there were no floods found. And then the paleofloods at the end of the Ice Age. And we're talking from 13,000 to 75,600. And they're covering the features. So except for one bench that is outside a little bit, they all fall between the boulder lag and the terraces. There was one bench that, didn't behave and we didn't know what to do with. Another case, Glacial Lake Passaic in New Jersey. This is close to where I grew up, and it's a work in progress. George Hamel Cook, he was the state geologist and the president of Rutgers, and he was the first one to find glacial evidence off the lake. There were shorelines, and he was the one to establish it, and he published a report. And these two people came after him. One of them was the supervisor of Brett's, and they're associated with him, Chamberlain. And anyway, they put up a report, Lake Passaic, an extinct glacial lake. And it was published in a very large report from 1893. So after 13 years, they established the lake. And this is one of the most industrialized areas next to New York. And houses started going up there. And so this is a really good record that we have from 100+ years ago. But if this is an extinct glacial lake, where did it go? Where's the water? I mean, there's a lot of glacial lakes that are still existent. So Scott Stanford, he's from the New Jersey Geologic Survey. He was the one that worked on it, and he reconstructed the spillways. And as I said, the spillways are now predominantly built. I'll show that in a few slides. And you can see there were 3 different glacial stages to Lake Passaic. It was the Chatham stage was the first one. There was the Moggy Hollow stage and the Great Notch stage. I'll relate to the last one. And as I said, Scott Stanford is responsible for that. This is what is left of the Great Notch, a road, some kind of weird outcrop of bedrock and a giant basalt protruding rock. And this is the Great Notch Inn. And it's quite disappointing that they just bulldozed it down this breach. But okay, we'll work with that. This is the third river, the last spillway. We could see it's completely urban and suburbia. It's urban, it's in people's backyard. It's not something impressive. It's looks man-made, almost like a canal, not something impressive. Houses, roads, industry, the cities of Montclair and Clifton. But then we have the crown jewel. There's one protected land, 20 acres. It's called the Alonzo Banza Nature Preserve. It's between Montclair and Clifton. It was given to the local residents as a gift in the 1970s. And they protected it. They didn't know about anything about the glacial history it has. It's for them, it's a nice park that they bring their dogs to, play around. But unfortunately, fortunately for us, this is the only thing that is left really well preserved. We have a misfit stream of the spillway, which is the third river. We can see how tiny it is relative to the valley. These are the houses here of Montclair. On the other side, can't see them. It's the houses of Clifton. We have very large boulders within the channel that are well beyond the channel's competence. We had Hurricane Ida 2 years ago, and nothing moved. You know, it was about 40 cubic meters per second at peak flow. This was a flood that killed people, but it was not able to move the glacial era features. And we also have boulders far away up the valley, large boulders of granite and basalts that are not local. They're imported from upstream from the Great Nash. So this tells us that we could use it as some kind of reconstruction that we're doing right now. So you see this is a basalt, the one that is covered with a lot of greenery, algae and not algae, but moss. And granites here. Also, there's no granites. This is all soil and Rahway till. So this is all imported from upstream, probably as erratics. And we have several of those indicating the floodlines of the valley. So finally, when I connect all these case studies together, modern gauge peak floods versus model reconstructed dam break paleoflows, and we could see that some of them survived, some of them didn't. In the Ashalim that I showed you in the desert, there's the upper one. It was completely erased after 3 years. Nothing was left. The lower one still exists. The cave is up the river valley, and it exists. Nahal Oz still exists. Kfar Yoshua erased. Nahal Kishon had a very large flood afterwards, and it erased it. Lake London spillway exists in patches, Komoka Provincial Park. Lake Passaic also in patches. Whenever there's a park, it is preserved. But around it, it's all built environment. And what do these peak discharges and their present climate tell us about preservation? So desert flood evidence, where there's barely any precipitation, channels are not active, and you would expect things to actually be preserved for a long time. Vegetation recovery plays a key role in disturbing or erasing flood evidence. However, if the magnitude of a paleoflood is significantly larger than the modern flows, it's likely to survive, as the erosional depositional features are possibly far away from the active channel, regardless of the climate. And I will put a cautionary note because I only have 8 different spillways in 5 locations, and it needs much more to make big conclusions. So in terms of recovery, Nahal Oz was a good chance to go back 2 years, 5 years, and 7 years, and to see what happened. The spillway is still there. Vegetation took over, it recovered. We could see using remote sensing, we were able to show that complete recovery of the vegetation, but the spillway still exists. We returned there 2 years ago, 20 years after the flood. The misfit gully channel still exists. Vertical less walls up to 5 meters still exist, and the spillway still exists. This is not something that could be erased when you put a tiny gully and you put a giant flood into it. And finally, the human factor. Modern dam breaks are considered one of the most severe geohazards. Old constructed dams are usually receiving low safety scores. I don't know about Oregon, but in most states, the safety score of dams is C and below in the US, which tells you that their safety is compromised, usually because of age. And it needs to be a lot of money to bring back those dams to top-notch level when they were built, usually in the 30s all the way to the 50s and 60s. And the glacial dams themselves are unstable, as I said, due to climate change. So when a dam break flood occurs, there's usually a great effort by government agencies, NGOs, and individuals to restore the landscape to its pre-flood state. This means less field evidence for us, and the time to collect data if affected area is populated is relatively short. So if we're talking about a place that is close to a population or active fields, it's a matter of days until they restore it and the evidence are gone. So drone imagery and LiDAR can be very helpful tools. But even historic floods are not safe from being prime real estate for urban development and agriculture. And here we could see an example. This is the Upper Ashalim Dam. As soon as it happened, all the machinery went in and created another reservoir, basically to stop the water from leaking. This is the Kfar Yehoshua Reservoir. After 6 days, they felt confident enough that they could close the breach. And I'll conclude. Geomorphologists have a lot to contribute to dam break floods, whether modern or paleo. The engineers are concentrating mainly on the failed infrastructure, while we look mainly on the downstream flood effect. The breach is not a good representative of QP, peak discharge. Downstream flood modeling can achieve more accurate results. Climate or precipitation is a dominant factor in the preservation or destruction of dam break flood features. This work looked at 8 case studies in 5 different climatic zones, but a much larger body of literature is needed to find the appropriate indices to describe preservation or destruction with different timescales. And natural erosion and human activities are constantly erasing dam break flood evidence, modern and historic. This means that the geologic record is missing many flood events, that their mark on the landscape was short-lived. And the acknowledgements to the people that work with me on all these case studies.